Okay, we're going to talk about chemical symbols and formulas. First, we need to talk about atomic theory. So an atom is the smallest identifiable unit of an element, and an element is a substance that cannot be broken down into simpler substances. So here are some pictures of some elements, or some atoms. On the left, we have a picture of gold atoms, and on the right, these are xenon atoms that IBM wrote out in the letters IBM. And this was done, both of these were done with a scanning tunnel microscope. The xenon atoms in the IBM picture appear pointed, but they're not. They're actually round. That's just an artifact of the instrument. Okay, let's talk about Dalton's atomic theory. He came up with this in 1808. He said that each element is composed of tiny, indestructible particles called atoms. All atoms of a given element have the same mass and other properties that distinguish them from the atoms of other elements. Atoms combine in simple whole number ratios, to form compounds, and atoms are neither created nor destroyed during a chemical reaction. And then in 1897, the English physicist J.J. Thompson discovered electrons. What he did is he passed an electron beam through a cathode ray tube. In a cathode ray tube, the one side of it's positively charged and the other side is negatively charged. And when he passed the electron beam through the cathode ray tube, he saw that the beam was attracted to the positive electrode side instead of just going straight through the middle. So this meant that there has to be these electrons have to have some negative charge. But he knew that atoms were neutral. So he knew there had to be some kind of positive charge to balance the negative charge. So he came up with the plum pudding model. And that said that there's negatively charged electrons were small particles held within a positively charged sphere. So the negative electrons were plums, and the positive mass was the pudding. And then in 1909, Ernest Rutherford did the gold foil experiment, and he worked under Thompson, so he knew very well Thompson's experiments and theories. So what Rutherford did is he took alpha particles, which are 2 protons and 2 neutrons, so they're positively charged particles, and he passed them through a gold foil surrounded by a detector. And he thought, okay, the particles should go right through the gold atoms if their mass and charge was spread throughout the entire volume of the atom, such as in the plum pudding model. But that's not what he saw. He saw that most of the particles passed right through the foil, but some of them were deflected. Some were deflected at very large angles. So he thought, okay, what's going on? So again, he expected the alpha particles to go straight through the atoms, but that's not what he saw. He saw a lot of them were deflected. And so he said, okay, this is happening. So the mass and the positive charge must all be concentrated within a small portion of the atom, which is the nucleus here. So the alpha particles are hitting the nucleus and then they're being deflected. So he came up with the nuclear theory of the atom, which said that most of the atom's mass and all of its positive charge are contained in a small core called the nucleus. Most of the volume of the atom is empty space through which tiny negatively charged electrons are dispersed. There's many negatively charged electrons outside the nucleus, as there are positively charged particles called protons inside the nucleus, causing the atoms to be electrically neutral. Later work by Rutherford demonstrated the atom's nucleus contained both positive protons and neutral neutrons. So like I just said, protons are positively charged particles, neutrons are neutral particles, and these are both contained in the nucleus. The nucleus makes up more than 99.9% of the mass, but only occupies a very small fraction of its volume. So the nucleus is very dense compared to the rest of the atom. And then the electrons are widely distributed, but have a much smaller mass. So here's just a picture. As you can see, here's the nucleus in the center with protons and neutrons. And that contains 99% of the mass. And then the electrons are widely dispersed around the nucleus. So the volume of an atom is mostly empty space. Here's just a chart of the subatomic particles. So there's three subatomic particles: protons, neutrons, and electrons. The atomic mass unit, or AMU, is defined as 1/12 the mass of a carbon atom containing 6 protons and 6 neutrons. That's just what you see here. We don't count the electrons towards the mass of the atom because it's so much smaller than the mass of the protons and neutrons, it's negligible. So if you look here, the mass of a proton is about 1.67 times 10 to the negative 27 kilograms. Neutron's about the same, 1.67493 times 10 to the negative 27 kilograms. So the mass and AMU of a proton is 1.0073. For a neutron, it's 1.0087. But if you look at an electron, so they're pretty comparable, right? They're almost exactly the same. But if you look at an electron, its mass in kilograms is 0.00091 times 10 to the negative 27. And an AMU, it's 0.00055. So you can see it's just a very small fraction of the mass. And that's why we don't count it towards the mass of an atom. And then we talk about charge. Protons are +1 charge. Neutrons don't have a charge at all, and electrons are -1 charge. So for every 1 proton and 1 electron, their charges cancel. Let's just do a brief review of electrical charge. So positive and negative charges attract. Positive and negative charges repel. And positive and negative charges cancel. So for 1 positive charge and 1 negative charge, you have a overall neutral charge. Okay, now let's talk about element symbols. So each element has a name and then a symbol, a one or two letter symbol that is corresponded with it. So here's just some examples of element names, their symbols, and the source of the name. So for example, uranium, its symbol is U. It's named after the planet Uranus. Titanium, its symbol is Ti. And it's named after the Titans from mythology. Magnesium is named after magnesia, a mineral. Curium is named after Marie and Pierre Curie. And here are some more elements and symbols. I will, just to go back to this, I will post on D2L a periodic table which will show you the elements and symbols you're responsible for. It's a periodic table, and there's a red line along a bunch of elements. Everything above the red line, you're responsible for knowing the name and the symbol of those elements. Again, I will post that on D2L for you. Okay, now let's talk about atomic number. Atomic number is the number of protons in an atom. And the number of protons in an atom's nucleus defines that element. So every single aluminum atom has 13 protons. Every single one. If it had 14 protons, it would be silicon. We represent the atomic number by the symbol Z, which we'll talk about more later. And then again, if an atom is electrically neutral, the number of protons should equal the number of electrons. Okay, let's talk about this. So silicon, for example, its symbol is Si, and its atomic number is 14. So that's the number at the top of the box. So that means silicon has 14 protons. That's the definition of silicon. It's an element with 14 protons. Potassium, its symbol is K, and its atomic number is 19. So every potassium atom has 19 protons. Gold symbol is Au, and its atomic number is 79. Antimony is Sb. Its atomic number is 51. So when you look at a periodic table, this is how you read it. At the very top will be the atomic number. And again, that's the number of protons. Then you'll have the chemical symbol. Then you'll have the atomic mass, which we'll talk about later. And then you'll have the name at the bottom. Not every single periodic table has the name, just so you know, but every periodic table will at the very least have the atomic number, chemical symbol, and atomic mass. Okay, let's talk a little bit about the periodic table. So there's groups and periods. So a group is a vertical column of elements, and they all have similar properties. We have the main group elements, or the representative elements, and those are groups 1A through 8A. And those are on the far left and far right of the periodic table. And then we have the transition elements or transition metals. And those are groups with the number and then B. And then a period is just a horizontal row. So if we look here, these two columns, and all of these are main group elements. And then these elements in the center, those are the transition metals. Okay, so this periodic table also shows you what elements are metals, nonmetals, and metalloids. So anything that's in this tan color, that's a metal. As you can see, that makes up the vast majority of elements. Most of them are metals. And they're basically everything on the left of the periodic table, except for hydrogen. Then the nonmetals are green. There's just a couple nonmetals, and they're all on the right of the periodic table. And the metalloids kind of divide the metals from the nonmetals, and those are purple. So let's first talk about metals. Metals all are good conductors of heat and electricity. They're all malleable, which means they can be pounded into flat sheets. Think about aluminum foil. That's just aluminum atoms that are pounded very, very thin. They're very ductile. They can be drawn into wires. So if you think of copper wires, they tend to be shiny. They tend to lose electrons. They tend to have high melting points. And they're all solid at room temperature except for mercury. Mercury is a liquid at room temperature. So, you could make pretty good generalizations about all metals, right? If I gave you a metal, you should be able to tell me, okay, this is a metal, so it's a good conductor of heat and electricity. It's very malleable, it's ductile, it's shiny, it probably loses electrons, it probably has a high melting point, and it's a solid room temperature, unless it's mercury. And then now let's talk about nonmetals. Again, these are these green elements on the right of the periodic table. These have much more varied properties. Some are solid at room temperature, other are gases, and there's a couple liquids too. They tend to be very poor conductors of heat and electricity. They tend to gain electrons. They tend to have low melting points, and they also tend to have low densities. So unlike metals, where we can definitively say a lot of things about them, we can't definitively say a lot of things about nonmetals. So if I gave you a nonmetal, you wouldn't be able to tell me, okay, this is definitely a solid, like you could with metals as long as it's not mercury. Or this definitely has a low melting point, things like that. Finally, let's talk about metalloids or semi-metals. And again, they run along the barrier between the metals and nonmetals. Like I said, they're also called semi-metals. They have very, very mixed properties. But the main thing to know about the semi-metals is that they're called semiconductors, which means they have intermediate electrical conductivity, which can be controlled. So that's why we use them in electronics. So for example, silicon is a semi-metal, and we use it as a semiconductor in a lot of our electronics.